Let's talk about different ways of expressing the concentration of a solution. In Gen Chem 1, hopefully you covered the concentration unit of molarity. If you did not, we are going to go over it again briefly here, but I'm mostly working under the assumption that you've seen it before, so I'm going to kind of skim through it fairly quickly. So molarity, just in case you did not see it before, or in case it's been a little while, maybe. The molarity of a solution is the number of moles of solute in the solution divided by the number of liters that the solution occupies. So it is moles per liter. How many moles of stuff for every liter of solution? That is the molarity. Molarity is by far the most common unit of concentration that we are going to use in this class. It is by far the most common one used by chemists. We're going to look at a few other concentration units, like I said. Most of the other ones are very specialized. So most of the other units, like parts per million and parts per billion, for example, those are mostly used in fields where we're dealing with very small concentrations of things, like environmental chemistry, for example. Molarity is a much more generalized unit. You find it in lots of different places because it's kind of an all-around useful unit of concentration. So just to get a little bit of practice here using molarity, this question asks, what is the molarity of a 3.5 liters of a sodium chloride solution if there are 100 grams of sodium chloride dissolved in the solution? I would like you to pause the video here and give this one a try, see if you can work out the molarity, and when you think you got it worked out, unpause the video, and I will work through it on the screen with you. So go ahead and pause the video now. Okay, hopefully you gave that a try. This one is pretty straightforward. We're just looking for the molarity, which is normally written as capital M, uppercase M. And to find the molarity, we need the number of moles, which is often shown as a lowercase n, and the number of liters. That's what we need to find the molarity. Really, for all of these concentration units, we can think of them as being two different things, one thing over another thing, because that's really what they are. They're all just an amount of solute divided by an amount of solution. Now, what those amounts are, specifically the units of those amounts, will be different for each one. But really, every concentration unit is just a certain amount of solute for a certain amount of solution. It's always those two things. And so most of the time when I am working with questions like this, where I'm either trying to determine the concentration of a solution, or I'm trying to determine something else about a solution that is related to the concentration, I like to think of it in terms of the concentration being these two things, kind of thinking of them separately like that, because it will often help. In this case, since this is a very simple example, really we're just going to find these two things. We're going to find the number of moles, and we're going to find the number of liters, and the number of liters is already given to us. It's 3.5 liters. So all we have to find is the number of moles. So the number of moles is going to be directly related to the mass of the solute that we have in there. So if we have 100 grams of NaCl, we will need the molar mass of sodium chloride, and I don't remember that off the top of my head. So sodium is essentially 22.99, and chloride is 35.45, so that is 58.44 grams grams per mole. And so if I go ahead and do that division, that is 1.71 moles of NaCl. So then the molarity would just be 1.71 moles divided by 3.5 liters. And that is going to be essentially 0.489 moles per liter. Okay. One of the other fairly common units is the mass percentage. And the mass percentage is very straightforward. This is just the mass of the component, the mass of the thing that you are interested in, divided by the total mass of the solution. Now notice here, this doesn't necessarily have to be the mass of the solute divided by the mass of the total solution. Usually it is. Most of the time it is. But it doesn't have to be. You could actually determine the mass percent of the solvent, and that would be perfectly legitimate, but usually it is the solute, since that's the thing you're interested in most of the time. So it's the mass of the thing you're interested in divided by the total mass of the solution, so that includes everything, solutes and solvents, times 100. That is the mass percent of that particular component of the solution. Now, parts per million and parts per billion, which are other concentration units, like I mentioned just a minute ago, these are more commonly used in fields of science where you're dealing with very small concentrations. So in environmental chemistry, for example, you might be investigating the concentration of some kind of contaminant in a river or a stream somewhere. Hopefully, you would need to measure that contaminant in parts per million or parts per billion. If you were measuring it in, if you needed to use a larger unit, then that stream is probably in really bad shape. So hopefully you're using parts per million and parts per billion, because these are most commonly used for very low solute concentrations. The reason for this is the parts per million and parts per billion are exactly the same as mass percentage, except instead of multiplying the ratio of the thing you're interested in divided by the total mass by 100, you multiply it by a million or a billion, just depending on which one of these you're using. So parts per million is just the mass of the thing you're looking at divided by everything times a million, and parts per billion is the mass of the thing you're interested in divided by the mass of everything times a billion. So essentially what this multiplying by a really large number at the end does is it takes a really tiny concentration that you would otherwise need to describe as, like 1 times 10 to the negative 6, mass percent or whatever, and it's instead is now 1. It makes it a much more easily manageable number. So you would have 1 parts per million instead of 1 times 10 to the negative 6 mass percent. It makes it easier to handle the numbers, these parts per million and parts per billion. But in terms of the math, they are exactly the same. The only difference is that number at the end. Either 100 for the mass percent, or a million or a billion for parts per million and parts per billion. So let's look at an example here. So this question asks us, what volume in milliliters of a soft drink that is 10.5% sucrose by mass contains 78.5 grams of sucrose? And it tells you here that the density of the solution is 1.04 grams per mil. Okay, just like this, the one we did a minute ago, I'd encourage you to pause the video and see if you can work this one out on your own. This one is definitely a bit tougher than the first one that we did. It's not terrible though. It's not, you know, it's not like a need to, you know, takes an hour to work out the math or anything like that. It's just, it takes a little bit of thinking through the units and what you're looking for, and looking through the data that's given to you. But it's definitely doable, so I would encourage you to try to work this out on your own. There are actually a couple different ways that are really the same way, they just look different, that this can be done. So give that a shot, and we'll work through it together when you come back. Okay, so I hope you gave this one a try. One of the key things to this question is actually looking at what am I trying to find, what am I actually trying to find, and what do I know that will allow me to find that. Thinking through the problem is really one of the biggest parts here. So what we're trying to find is a volume. We're trying to find the volume of the soft drink that would have this much sucrose in it. Now, if you really focus in on that volume and you're only looking at things with volume, you probably will go down some rabbit trails that are not going to be terribly helpful. Instead, what you should realize is that we're given the concentration in a mass percentage. And we're also given the mass of the solute that we have in our solution. And so what we're going to do is, if we look at the concentration, the equation for that concentration, it says the mass percentage of the component, which was something that was given to us in the problem, is equal to the mass of the thing that we're looking for, which was also given to us in the problem. That would be the 78.5 grams of sucrose. So we have this much of the solute in our solution. So the mass percentage is equal to the mass of the thing that we're interested in, divided by the mass of everything, times 100. Now this mass of everything, that is directly related to what we're looking for. Because remember, we're looking for the volume of the solution. So we're looking for the total volume of the solution. And now you might be thinking, well, wait a second. We want the volume, but this is the mass of the solution. To that I would say, correct you are. Those are not the same thing. But right at the very end here, we're given the density. So if we can figure out the mass of the whole solution, then we can use this density to convert that mass into volume. So again, the hardest part of this problem is not the math, for sure. The hardest part is working out your pathway from what you're given, because you're given quite a few different things here. Finding that pathway from what you're given to what you're trying to find. So hopefully I explained that well enough that you can see what we're going to do here. So the first thing we're going to do is we're going to use this equation to find the total mass of the solution. And we could do this a couple different ways in terms of the algebra. I think the easiest way is to go ahead and do the algebra first. So essentially what we're going to do is we're going to multiply both sides by the total mass of the solution, which will essentially make that disappear over here and pop up over here. So we'll have the total mass. And then we'll divide both sides by the mass percent. And so really what we're doing here is we're kind of having these two swap positions. So we divide both sides by the mass percentage, so that goes away over here and shows up in the denominator over here. Okay, so then if we go ahead and do that here, so the total mass is going to be the mass of the thing we're interested in, which is the 78.5 grams, divided by the percentage, which is 10.5 times 100. So if I go ahead and do that math I get 740. Let's see, I'm really only, well, I won't do sig figs until the very end here, so I'll only have three sig figs at the very end, but right now I'm going to go ahead with 747.62. And that would be, let's see, what would the units be on that? It would just be grams. Yeah. Because this is unitless. It's just a percentage, and so is this. So it would just be grams. Okay, so I know that the total mass of my solution is 747.6-ish grams. And so then to find the volume, I would just take that, and I will use the density as a unit conversion factor. And so I know that for every 1.04 grams, I will have 1 mil. And so that's just going to decrease that number slightly down to 700, and we'll say 19. Oops, almost said grams. 719 milliliters. And there we go. So that is the volume of the solution that would have 78.5 grams of sucrose in it. All right, hope that made sense to you all. Couple last units here that we will be using actually later on in this chapter. These are the mole fraction, and as we'll see in just a second, the molality as well. But first, the mole fraction here. This is very closely related to the mass percent, only now we're using the number of moles instead of the mass. So the mole fraction of a component is just the number of moles of the thing we're interested in divided by the total number of moles, and we don't multiply by 100 at the end. You can do that if you're looking for the mole percentage, which is a thing and is sometimes used, but we're not going to use it. If it's just the mole fraction, then it is literally just the fraction. It's just how many moles divided by the total number of moles. So that is the mole fraction. We'll use that a little later in one of the equations involving, well, we'll get to that. Well, we'll talk about it later. The other unit that I mentioned just a second ago is the molality. This is probably the weirdest one. It is the weirdest unit that we're going to come across. This is the total number of moles of solute divided by the kilograms of solvent. So it's kind of a weird one. Up to this point, we've had kind of similar units on top and bottom. But now we have moles of solute over kilograms, not of the solution, but kilograms of just the solvent. So moles of solute divided by kilograms of solvent. It is really only used in one situation, but that one situation is actually very useful. So you do need to know how to use it. We won't use it in really any other situation, any other equation, but in this one situation, which is freezing point depression and boiling point elevation, we do need to use the molality. So let's look at an example of that. So this is example 11.2 from your book. It says the antifreeze in most automobile radiators is a mixture of equal volumes of ethylene glycol and water, with minor amounts of other additives that prevent corrosion. What are the A, mole fraction, and B, molality of ethylene glycol in a solution prepared from 2.22 times 10 to the third grams of ethylene glycol and 2 times 10 to the third grams of water, which is approximately 2 liters of each. So we're going to find both the mole fraction and the molality. So the first one here, the mole fraction, pretty straightforward. Just moles of the thing we're interested in which we are going to say is the ethylene glycol, because we have to pick one. So the ethylene glycol is what we're going to have here as our moles of component divided by the moles of everything. So to find that, we actually need to figure out the molar mass of both of our components here. Water, you might not have it memorized, but I've used water enough that I know that is the molality of water. Ethylene glycol, on the other hand, I do not have memorized. So let's see. Carbon is 12.01, and we have 2 of those. We have 6 hydrogens. Those are 1.008. And we have 2 oxygens, which are essentially 16 each. So that gives us 62, we'll say 0.01. It's not the most precise molar mass, but it'll work for us. Okay. So if we go ahead and work out how many moles of each of things we have, for the water, we're told we have 2,000 grams, because that's what 2 times 10 to the third is. So we're going to have 2,000 divided by 18.02. And just for the sake of space, I'm not going to write that out as a unit conversion, even though it is. Just when we're dividing, excuse me, dividing the number of grams by the molar mass gives us the number of moles. So that is going to be 111, essentially, moles. 110.987, but we'll round out to 111. The ethylene glycol, that is 2,220 grams. Divide that by its molar mass, which is 62.01. I'm just going to call it EG. That has 35.8 moles. Okay, so then the mole fraction of ethylene glycol, and I guess it does specify of ethylene glycol there, so we didn't actually just pick. It did specifically tell us for the ethylene glycol. So anyway, the mole fraction is going to be 35.8 moles of the ethylene glycol divided by 111 plus 35.8 for the total number of moles. And we do not multiply it by 100, and so we are going to get make sure I put that in my calculator correctly. That is 0.244, we'll say, is the mole fraction of ethylene glycol in that solution. And it is a unitless value, because it would actually have moles as the unit on both sides here, and so they would cancel out. Okay, so that is the first part. Oops, the first part there. I would like you to try the second part. Try to work out the molality of that solution. And feel free to use some of the values that we had up here in part A to help you work out that answer. So go ahead and give that a try. Okay, I hope you tried that. Because we worked out part A first, we really don't have to do anything other than the final calculation here. Because if you remember, the molality, which is normally the lowercase m, which I know is confusing because it's also used for mass quite often. There's a limited number of letters, unfortunately. Well, actually, I should say fortunately. Life would be rough if there was an infinite number of letters. So anyway, it is normally written as the lowercase m. And so that is the number of moles of solute divided by the kilograms of just the solvent. And we essentially already know both of those. We already know the number of moles of solute. That's 35.8. We calculated that in part A. The kilograms of solvent, technically we don't know, but it's a very easy calculation to find that because we're given the number of grams of solvent. Now, in this case, since they both have equal volumes here, it's one of those situations where, you know, they're really kind of both the solvent because technically we have equal amounts of both. But because we have more moles of the water, we're going to say that the water is the solvent, and that is technically correct here. The water is the solvent in this situation. Usually you can tell by the volume which one is the solvent, and this is just one of those cases where you can't. But because we have a lot more moles of the water, this is the solvent. So the kilograms of the solvent is 2, because we have 2,000 grams. If you want to go ahead and do the calculation there, and hopefully you did when you work through this, you will find that it is 2 kilograms. And so the molality will be something like 18, if I remember correctly. 35.8. Yeah, 17.9. Molal. Moles per kilogram. Okay, and I think we have, just one more here. I know, I'm sorry this video is going a little bit long, but I want to get these all in instead of breaking them apart. So last question here. Calculate the mole fraction of solute and solvent in a 3 molal solution of sodium chloride. So again, the lowercase m here, that is molal, not molarity. Molarity is uppercase m. So what this is telling us is that we have 3 moles for every kilogram of solvent in this solution. And they also tell us that we have sodium chloride, which will be useful. So again, anytime I'm doing a question like this, I'd like to think about it in terms of finding 2 different things. So in this case, I'm trying to find the mole fraction. If I just think of it in terms of the mole fraction, it might be kind of hard to solve this. But if instead I think, okay, I'm looking for the mole fraction, but I know the mole fraction is made up of 2 different things. It's made up of the number of moles of the thing that I'm interested in, which is the sodium chloride in this case, divided by the total number of moles. So I'm not trying to find the mole fraction really, I'm trying to find these other 2 things, and that will allow me to find the mole fraction. So what I'm going to do is I'm just going to go ahead and say, because it's not actually told to me in the question what the total volume of the solution is, it just tells me the concentration. And truthfully, we don't need to know, because that's the mole fraction will scale. Like if you have 1 liter of this or you have 20 liters of this, the mole fraction is going to be the same. It's not going to change with the total amount. So we're just going to set a value and say this is the solution that we have. And so we're just going to go ahead and say this. We're going to say we have a solution that has 1 kilogram of solvent and 3 moles of solute, because that'll just make it easier for us. We could just as easily said we have a solution where there's 6 moles and 2 kilograms, but why would we do that? As long as the molality stays true, we could have any overall size of solution. So this actually already tells us what the top part of our fraction is going to be for the mole fraction, because we just said we have 3 moles of the solute. So really the only other thing we need to figure out is how many moles of solvent do we have. And thankfully, we know how many kilograms of solvent we have, because that is built into the molality. So if we have 1,000 grams of water, what that means is we have 50, oh yeah, I should have known that off the top of my head, 55.5 moles of water, because water has a molality of, a molarity of 55 molar. There are 55.5 moles of water per liter. So anyway, so we know how many moles of solute we have because it's given in the molality here. And we know that total in our solution we have 3 plus 55.5 moles. And so the mole fraction is going to be, make sure I get my parentheses in there. It is, let's see, 0.051. By the way, it's probably, you could probably work out what went wrong if you did this by accident, but when you type this into your calculator, if you don't type it in like this with the parentheses, you will get a very wrong answer. If you just type it in 3 divided by 55.5 plus 3, the calculator is going to do the division and then add 3 to it. So you really need those parentheses in there so that it keeps that denominator together. All right. I know that was kind of a long video. Sorry about that, but we are finished with that section there. And so we're going to pick up next time with the colligative properties and the equations that we use for those, which directly involve 2 of those units, concentration units that we're just looking at, namely the mole fraction and the molality. So we'll pick up there next time.